Welcome to Westpak's Packaging Dynamics webinar number 2. It is entitled Defining and Quantifying the Distribution Environment Through Which All Products Must Travel. I'm Greg Swinghammer and will be your moderator and webinar organizer today. Before we get started, let's take a moment to ensure that everyone is ready and familiar with the webinar control panel. First, you should have a control panel on the right side of your screen. You may minimize this panel by clicking on the orange arrow button in the upper left-hand corner. You may expand the panel by clicking on the same button. Secondly, you have the ability to submit questions using the chat pane located near the bottom of the control panel. We will be answering a few questions during the webinar. However, if we are unable to address your question during the webinar, one of our presenters will follow up with you via email afterwards. Today's webinar video and slide deck should be available on Westpak's website tomorrow. With that, let's get started. Today's presenters are Schueneman and Edmund Tang. You may remember Herb from the last webinar on riveting revisions of ASTM standards. Edmund is a lab manager here at Westpak and a lecturer on packaging at nearby San Jose State University. Edmund, you're our first presenter. Take it away.
Thanks for the introduction, Greg. Right here is the agenda of what we will be discussing today. So we will begin with just a little review of webinar number 1, because it was 2 months ago and we covered quite a few topics, and we just wanted to emphasize the important topics that we thought you should know for this webinar. Secondly, we're going to review or introduce the 5-step method, and the first step of the 5-step method is to define the environment, and that is the focus of this webinar. Followed by, we're going to discuss the predefined distribution environment, and then we're going to talk about obtaining and collecting live data if you were to do, let's just say, a distribution environment study yourself. Next, Herb is going to talk about just a review of webinar number 1.
Thanks a lot, Edmund, and welcome to this second in a series of 5 webinars that we ambitiously try to make protected package design engineers out of everybody. So during our first webinar, as Edmund mentioned, we attempted to lay the groundwork and define the terms that will be used consistently throughout this 5-part series. Included with the material that you can find on our website is a list of terms that will be important to have handy if you are not comfortable with some or all of these. We encourage you to refer to this list whenever you hear a term that you are not comfortable or familiar with. In particular, we want to make sure that everyone is comfortable with the different methods of presenting the data, especially the time domain versus frequency domain formats. Quite simply, the time domain tracks some change in force or excitation or similar as a function of time. The frequency domain is the inverse of the time domain and often displays amplitude or excitation level as a function of frequency. We call this frequency domain a spectrum. And you can see examples of both time domain and frequency domain data on slide number 3 that's currently showing. Edmund?
All right, so in addition to that, we also talked about just the common packaging dynamic hazards that a package or crate or just a shipping box would typically see when you ship something from A to B. And the first one is vibration. And the thing about vibration is that it's completely unavoidable. No matter what, you're always going to see vibration. Second hazard would be shocks or drops or impacts. When you drop a package or when you bump a package, it's also a shock or a mini drop. And then lastly would be a compression hazard, like for instance in the warehouse or just in a vehicle when you're stacking boxes on top of your box, to say the least. Herb?
Well, thanks, Edmund. Just a comment on that previous slide. I always had the feeling that the vibration was no big deal, and the impacts are really the thing I should focus on because they cause the damage. It turns out to be perhaps just the opposite, because exactly as Edmund pointed out, vibration is unavoidable, whereas impacts are a probability function. Sometimes they happen, sometimes they don't. Moving on, it's an important concept that we introduced last time during the last session, has to do with recognize the difference between an input and a response time domain function or happening. The response of any spring mass system to a dynamic input, shock or vibration are typical, is likely to be different and sometimes vastly different than the input. So it's critical to understand why a difference exists between input and response in the first place, and to ascertain what this information is really telling us. We'll be referring often to both the input and response functions throughout this webinar series, and hopefully can explain clearly why these differences occur and exactly what the data is telling us. For the time being, we would be very happy if everyone simply understood that there is, in fact, a distinct and normally a very large difference between these two, and that we should strive to be careful not to confuse them. And here on this plot, you see a representation of the input on top in the blue trace and a response function below that. This might be a typical impact function on a shock test machine or something like that. So one of the important things is know the difference between an input and a response. Edmund?
Thank you, Herb. So in the previous slide, Herb talked about input and response, more specifically for a drop or a shock. And with this slide here, we have a chart, and this chart is specific for vibration input and response. So on bottom on this chart, it's known as a transmissibility plot. And in the transmissibility plot, there's three very, very distinct zones or ranges. The first zone is the coupling zone, where the response is almost equal to the input. So whatever your truck is seeing with vibration-wise, the same thing your unit is seeing vibration-wise. Second is the amplification portion of the zone. And this is when resonance occurs. And what you know about resonance is that it's a certain frequency that your spring mass system will pretty much have the greatest amplification, and all spring mass systems will resonate at the resonant frequency because they pretty much can't do anything else. Why you're concerned about this is because in this zone is where damage occurs to your product, usually with fatigue because it's vibrating at that certain resonance for a long period of time. And the last zone in green is the attenuation zone. And in this zone, the response is less than your input. So you could also say this is a safe zone. And this is, when this happens, your vibration is quote unquote protected, to say the least, or mitigated. And Herb will talk about the next slide.
Thanks, Edmund. Now that we have some basic definitions and concepts under our belts, I hope we do, we can lay out the steps necessary to go from here to a completely tested and optimized protective package system. It's important to understand that this protective package system is what we're focusing on. This, of course, starts with the now famous 5-step procedure for protective package design and testing. This procedure was initially conceptualized in the late 1960s, early 70s by people like Bill Kipp, formerly of Landsman Corporation, and perhaps others, who were then employed by MTS Systems Corporation. And they did this as a method of simplifying the use of damage boundary shock fragility assessment and resonant search testing for vibration sensitivity analysis. It was quite successful in its intended purpose and has been widely used in the intervening 40 years or more. When Landsman Corporation was formed in the early 1970s, those folks incorporated a 6th step in the process in order to avoid some legal problems, I guess. But this 6th step, which was referred to as a product improvement feedback, was fit in between the 3rd and 4th steps of the original 5-step procedure. Confused yet? Don't be. Both the 5-step and the 6-step procedures are widely recognized and lead you to exactly the same end result. But you can see them listed here. And the first one is to define the environment. That's what we're going to be focused on today. And then next you define product fragility or sensitivities of the product, really. And then you look at the performance characteristics of various cushions or mitigating mediums, call them. Then you actually do your package design and then test it. So it's a relatively simple thing that was originally called the cookbook, but the 5-step was the name that really stuck. Edmund, can you continue?
So the first step in the 5-step method is to define the environment. I'm not going to talk too much about this step because this is pretty much what the whole webinar is about, and we have separate slides for different topics regarding step number 1. But just in general, the step characterizes the package's distribution environment. When you think about a package or a crate or a product, anytime you ship it, again, from point A to point B, it's going to always encounter some type of environment. So this step is pretty much telling you what type of environment will it encounter and what does it have to face in order to be pretty much safe during shipment. Herb, step 2.
The second step is to identify the sensitivities of the product. We don't want to limit it to just a few things. We want to know whatever the product is sensitive to. So we want to identify where and how the product fails in terms of inputs such as vibration, which is considered to be continuous, drops, which is they're considered to be discrete events, temperature and humidity, again, events that come and go, compression, top load compression normally, and altitude or pressure differentials, also part of the distribution or shipping environment. So in the next webinar, we'll go into this process in depth and let you know the exact procedures for defining product fragility or product ruggedness, as we like to call it. Edmund?
Next step, step 3, is cushion material performance. So when you're looking at cushion material, you're definitely trying to quantify something. And more specifically, when you're quantifying shock performance, it means that you're seeing what the response of your unit is after you drop your product on this cushion. And then secondly, when you quantify vibration performance, it means the amplification and attenuation plots of pretty much what gets charted on your resonant frequency. And when you think about cushion materials, it could be pretty much anything, from foam to corrugated pads to thermoform shapes to molded pulp to air cells, even a water paper that's wrinkled up on the bottom of your package. That's also a quote-unquote cushion system. It's not as engineered and can't be designed as well, but for the most part, it's still a cushion. Next, package design, Herb will talk about this.
Thanks, Edmund. The fourth step in this 5-step procedure is to actually design the system that you want to protect the product. So it's more art than science. I think would probably be a good way to define it. But the information necessary to do this actually comes from the previous 3 steps, and if properly done, will actually optimize the protective package system, and that's our whole focus, to get that thing to be optimized. So Edmund, can you take us to the 5th step?
The fifth and last step of the 5-step method is to test your product and package system. So when you're testing your product and package system, what are you trying to tell yourself? What are you trying to validate? You're pretty much trying to tell yourself that the package that I designed in step 4 validates everything that I tested for in the previous steps. And what this means specifically is for during the drop-in impact testing, you want to make sure that when you drop your product, it doesn't see its critical acceleration levels. And during vibration testing, you're trying to validate the fact that at the product's resonant frequency, you're actually in attenuation, which means that your amplification that was originally 10x might now be 1x. And then same thing for temperature, humidity, and pressure differentials. With altitude, you're just validating that your package works in these conditions. And at the end of the day, if the job was done correctly, an optimum package system now exists for this product. And this takes us to our first break. And just want to know, Greg, do we have any questions at this point?
Thanks, Greg. Let's continue now with our deep dive, if you will, into the 5-step method. Now, the first step in this process is to define the distribution environment. By this we mean it is necessary to quantify those elements or hazards of the environment that are likely to cause damage to the product. It's important to emphasize the fact that metrics are necessary. You have to put numbers on it. This is not, in other words, it's not sufficient to say that the drop height is severe or moderate or low. It is necessary to put the exact quantities on all elements of the distribution environment, including impacts, so that they can be reproduced in the laboratory specifically and repeatably. Edmund, over to you.
So when you define a distribution environment, you're looking at specific hazards that your package might see when you're shipping it. And for that, what it means is that you're definitely going to see vibration because your package will go on a vehicle. And during that, you're definitely going to see some drops because your package will be either handled by a human, which is manual handling, or just a forklift with small bumps here and there. It's probably going to be stacked somehow, some way, either in a warehouse. And that's where compression comes in, or also when you're shipping it on your vehicle. And there's definitely going to see temperature, relative humidity, and altitude extremes and differentials as well. Herb?
Thanks, Edmund. So why in the heck is this important? The reason why it's important to metricize or assign numbers to each of these hazards of the distribution environment stems from the necessity to make the process repeatable and as accurate as possible. It's also important to remember that the end purpose of this process is an optimized package system, that is, a package that neither overprotects nor underprotects the product. And we refer to this as overpackaging or underpackaging. And underpackaging is normally very evident because it results in a damaged product at the end of the distribution cycle. As a packaging professionals, I'm sure that you always hear about these incidents. There's a damage in shipment problem, you hear about it. A much more insidious problem exists, I believe, with overpackaging. Overpackaging results in waste. It doesn't take a genius to look at our municipal landfill operations to determine that our society throws away way too much material. About a third of it packaging related. The five-step package development process is the best way that we are aware of to effectively reduce waste in our society, especially in the area of protective packaging. Another reason why it's important to study this process is that the supply chain distribution costs represent a majority of the delivered costs of most products. This includes the cost of packaging material itself, but also the logistics are normally far greater than the packaging material costs. It costs more to ship it than does to pack it. Optimizing logistics through proper protective package design and testing is the best way to minimize the total supply chain distribution cost for almost all products. So that's why we study it, that's why we try to metricize it. Edmund?
So to reiterate what Herb just said, how to metricize the distribution environment, we have, you could say, a conceptual, visual picture of the 4 packaging cases for a product. So the first thing that you're definitely trying to quantify is that black bar on the left side. That's known as environmental severity. So without that, knowing what pretty much how harsh your distribution environment is, it's impossible to design an optimum package system. So when you look at these 3 cases or these 4 cases, case 1, you're designing a package system for a product, and it's adequate and it does its job. So okay, you're decently happy. Case 2 is when you underestimate your distribution environment, and then what happens is that you have underpackaging. So this is probably the worst case for any any suppliers, like, oh, you now have damaged units which you can't sell, which you either have to replace or scrap. The third case is when you overestimate your distribution environment, and then you're dumping, pretty much you're wasting money for packaging, and like Herb said, you're having a lot larger package, and you're wasting money also in the supply chain, because instead of shipping 40 units per pallet, you're only shipping 25 units per pallet because the extra space is just used for void in the package. And the last case is when you actually determined the exact fragility of your product, and you know that it breaks at like a certain level, let's just say 40 Gs, and you tell yourself, this level is way too low. Let's put a little more money into this product, make it more robust, and cut costs and cut the packaging down. So then if that's the case, a lot of things happen. First thing that happens is that your customer gets a better product. And then a couple other byproducts is that you use less materials in packaging. And then finally, you have less transportation costs in supply chain as well. So case 4 is definitely the go-to cases, at least with this for packaging cases. Herb?
Thanks, Edmund. So we've been talking about metricizing these elements of the distribution environment. What in the world is the data we're looking for, and how do we quantify things like vibration and impacts? For the vibration environment, we are interested in the intensity levels of vibration, the frequency bands of which that vibration occurs, and the duration of the vibration input during a typical shipment cycle. We know that vibration input comes from transportation vehicles, trucks, aircraft, rail cars, ships. That is, the intensity and frequency of the vibration input vary randomly with time. So we know that they are random inputs. Thus, we are interested in defining the spectrum, acceleration versus frequency, that typically results from typical vehicles. We know that these numbers will vary depending on the load within the vehicle, the height above the floor where in the vehicle where the product might be resting, and a bunch of other variables. The job of quantifying the vibration environment involves measuring all of these variables and creating an envelope spectrum that adequately describes all of the possible intensity levels within the vehicle. And we'll be talking about envelope spectrum more shortly. The drop height is measured in terms of the height of the impact, the number of impacts likely to occur during any one shipment, and the orientation of those impacts. History has told us that the weight of the package system, and to some extent the package size, will have a large influence on the drop height of the package that the package might experience. The reason for this is that impacts during shipment are a people phenomenon. That's important to remember. People cause impacts. People throw packages that result in impacts. That's why most quantification of the drop height environment involves the weight of the package system being studied. The theory is that a larger and heavier package is harder to lift and throw any particular distance, and therefore the heavier or larger a package system is, the lower the drop height that may be experienced during shipment. Some studies have contradicted this assumption, but it is still a widely assumed to be valid. And this is exactly where the myth of the UPS gorilla comes in. Edmund, take it away from there.
Thanks, Herb. So when you also define the distribution environment in regards to temperature, what are you looking at here? Well, for temperature, you're looking at definitely hot and cold extremes, but then at the same time, you also have to remember that on a sunny day, it might be 100, 105 degrees outside. And that's what we feel. But then if your box and package, if it's inside a car or inside a vehicle, what happens is that it's pretty much like an oven. So instead of seeing what we see, the 100, 105 degrees, it's going to be a lot hotter than the actual outside temperature. And that's one thing that you definitely have to account for when designing a package system for your product. And with cold extremes, you don't really have to worry about that too much, just because it doesn't get colder in the vehicle as it as time goes by. For relative humidity, you definitely want to look if your product and your package is sensitive to moisture, to say the least. And then lastly, with altitude, we have pressure extremes. And with pressure extremes, we're definitely talking about aircraft. But here's a fun fact for you. Aircraft are typically pressurized to a level no higher than 8,000 feet. But then a truck, however, that goes through the mountain pass in Colorado can actually see up to 11,000 feet or more. And that's actually a little irony, because you would think that an aircraft will always see higher elevations than a truck. Not always the case. Next, Herb's going to talk about a predefined distribution environment in FPL 22.
And thanks, Edmund. One of the daunting tasks that always occurs to a package designer in this process to say, my gosh, I've got to quantify all that stuff? Holy cow, give me a break. Well, fortunately, it's not that bad. As it turns out, much of the distribution environment has been reasonably well quantified in the past. And we're going to go through a couple of those studies that help us in the process. One of the more famous ones, of course, was the Forest Products Laboratory study published in 1979 called FPL-22. FPL stands for Forest Products Lab. So it was report number 22, and it basically was a study of the hazards incident with the shipment of goods. One particular component of the study involved a series of container systems. One was a 43-pound box, a plywood box, a wooden box, and one was a 25-pound corrugated fiberboard box. And what they did was to measure the impacts using a recording device inside to a number of different shipments. There were 49 different trips for the wooden box and about 80 trips using the corrugated box. So there are actually a number of different container systems involved. But this particular study was very significant in that it didn't do any basic research, but actually just summarized research that had already been done. And on this next slide, we can actually see what that data was that they collected. So for the 43-pound box, there were approximately 800 impacts recorded. This box was shipped 49 times, which means a little over 16 impacts per trip were recorded. Some of the summaries that came out of that was that 50% of the impacts were in the base down orientation. The 99 percentile level, in other words, the level above which you get less than 1% of the events, was 36 inches. Only 18% of the impacts were above 14 inches, and the average or mean drop height was 6 inches. So it wasn't a very severe environment. The second study on the 25-pound corrugated container showed about 600 impacts over 80 trips, or an average of only 6 impacts per trip. As before, 50% of the impacts were in the base down orientation, and less than 6% of the impacts were above 36 inches. The one percentile level wound up being in the neighborhood of 40 inches or so, 30, I guess, 42 inches. So what you can see is that data on the impact environment has been reasonably well quantified already. Now this data came from again, studies that were done prior to 1979. So they're not the crisp, up-to-date data, all that kind of stuff. But the reality is that the distribution environment actually doesn't change all that much. People don't handle anything any different just because it's now 40 years after the study. So it is significant that this information was obtained without actually looking for it. On the next slide, we actually see a graphical representation of the distribution of these impacts as a function of the drop height versus the percentage of impacts that occurred at or above that drop height, actually at or below. So you see a pretty distinctive pattern, a linear relationship between the height of an impact and the percentage of drops above that indicated for various weights of package systems. So you have different slopes for these different weighted boxes. So this FPL-22 data was very significant, and it summarized this data. And what it told us was that a vast number of impacts occurred at lower drop heights, and that a very few occurred at higher drop heights above the indicated level. Now, it's very important to note, and we'll make note of this later on as well, that this is summed data. In other words, this is from like 800 impacts for the 25-pound box and 80 trips. and 49 trips for the other box. What we're really interested in is this data on a per trip basis, because that's exactly what happens to your container system when you ship it. So this data oftentimes was summarized in a way that isn't the most helpful to us and can be somewhat misleading. So I want to caution you to make sure that in the future you use always per trip data. Another interesting thing was that all of these trends were really verified during a mid-1970s study of the Federal Express distribution environment that I was directly involved in. And it absolutely amazed me that when I plotted the data, it looked like something right out of FPL 22, because again, the drop height hadn't changed because people hadn't really changed during the process. So a very interesting study. Finally, from FPL 22, we can see on this current slide another graphical way to present the data. And you can see here clearly that the vast majority of impacts were from the lower drop height, relatively few impacts exceeding what became what we call the design drop height for that particular weighted package. Design drop height is often referred to as the 1 percentile level. There's always outliers, they always exist, such as you can see a couple of those in the 43-pound box data. But it's important to understand that all of this data, again, is a lumped data format. That is, all of the data from a particular weighted box over a number of trips is averaged. And what you really want to do, what the package designer is most concerned about, is the average mean data for an individual trip. Okay, so that's one important distinguishing element between the data and mostly the presentation of the data from a previous history versus what we'll do today. Okay, Edmund, can you take it from there?
Thanks, Herb. So I'm going to talk about a second study that happened that, pretty much 20 years later, or not even 20 years later, like Herb said, FPL data was pretty much obtained somewhere in the 1950s. So you could think about it 40 to 50 years later, and this is when the Measurement and Analysis of Distribution Environment study happened, which is MAID for short. So the MAID study, pretty much, it was led by HP, and at that time, Paul Russell was the leader of this. And then it was pretty much a collaboration between 74 companies to, attempt to better quantify the distribution environment, to say the least. And then so here's just a short list of the pretty much the MAID study members. But if you look at it, there's, quite a few big names here that we have, or you could read yourself. I'm not going to emphasize anybody, to say the least. But going on, so in the study, it was from pretty much 1996 to 1999. So if you think about it now, 40 to 50 years later, our technology is better. And we're going to ask ourselves now, if we ship, again, a 25-pound box to simulate a computer, what will the results be this time? And the results of this was that the highest drop height found in all 40 round trips was 58 inches, and there was only one occurrence of this. And there was approximately 1,500 freefall drops recorded. Approximately 50% of the drops were recorded on the base down orientation. And then if you look at the next two numbers, that approximately 1.5% of the drops were over 36 inches, and approximately less than 5% of the drops were over 14 inches. And most drops occurred that's pretty much around the 4-inch mark. So data is always better analyzed in a table or in a graph here, and this is pretty much a graphical representation of what I just explained to you. So as Herbert likes to say, 95 percentile of the drops were around 4 inches, and then 1999 percentile of the drops were around 14 inches, and then lastly, that leaves 1% of the drops that were 1.5 above 36 inches. And then on the next table here, we have a comparison between FPL and MAID. So in this comparison, if you look at the drops that are greater than 14 inches, actually MAID is significantly less, which is 5% compared to the 18% that a 25-pound box saw and the 20% that the 43-pound box saw. And then if you look at the drops greater than 36 inches, is actually, pretty much, that's pretty substantial. Before in FPL 22, it was 6%, but now in Maid, it's 2%. So if you look at that, that's only a third of the drops that is actually over 36 inches. And then you might want to ask yourself this, okay, what's the reason why? And one of the main reasons why could be that now shipping companies such as FedEx and UPS, they have insurance, or they're more responsible for the shipments. And if anything is damaged, then they go back to the courier and say, hey, we tested according to this standard, and we were supposed to have, quote unquote, an undamaged shipment, to say the least. So that might be one of the reasons why the numbers actually dropped quite a bit between the 14-inch drop and the 36-inch drop. But if you look at the last column, the primary drop orientation still remained the base down, because it's just the way people carry packages. You always carry it face down, so therefore the chances of it dropping face down is always more likely than any other orientation, to say the least. And that brings us to our second break. Greg, are there any questions from the audience at this point?
Thanks, Craig. Let's continue with a discussion of how in the world is this data collected. It's important to recognize that there are three distinct processes or methods, if you will, to obtain environmental data. One is by observation, one is by damage reports. We get those all the time, and also by direct measurement. By far, the most common method today is a direct measurement, and that's exactly how we're going to continue. But I don't want to de-emphasize the fact that there are significant benefits to observation and by collecting the damage reports as well. Okay. So on the direct measurement, this next slide shows one of the processes, one of the pieces of equipment that is increasingly used to do this. This is a environmental ride recorder. This happens to be one called the Saver, and they're getting smaller and smaller with more and more capabilities as time goes on. In the days when I started doing this, they were the size of a huge lunch pail or bigger, and they weren't very handy devices. Today they're incredible. They have the capability of recording both impacts, impact mode as they call it, and a timed mode. During the impact mode, this is kind of interesting, shock levels above a predetermined amount will be recorded. So in other words, the shock has already passed, and it goes back, remembers 20% of its memory earlier, and it says, oh, better remember that one. That's pretty cool. In a timed mode, the recorder will turn on for a preset period of time over a preset time interval. So in other words, you might want to have it turn on for 10 seconds every 5 minutes, for example, and it measures typically vibration during that period. So they're really, really handy devices. The price is coming way down. They're incredible, the amount of stuff that they'll do. So the direct measurement tools then are important. And another important function is they'll also timestamp each occurrence. This shows an occurrence of an impact, for example. You see 3 or perhaps 4 different traces there. So they're recording a single event, or maybe in a vibratory motion, and they'll timestamp it. So this will allow us to predict exactly what happens when the truck runs over a curb, or a rail car is producing a coupling shock or something like that. But they'll also do the same thing and timestamp the humidity levels, the temperature levels, and the altitude levels as well. So it's hard to beat. These devices are really cool. And like I said, they're getting cheaper and cheaper. Edmund, can you tell us about the direct measurement type of data collection as well?
Certainly, Herb. So one of the data points that most people are concerned about is definitely drop data. And when you think about drop data, you're definitely concerned about the number of drops. How many drops did your package see when you shipped it out? The drop time, was it dropped when you picked it up, or was it dropped somewhere in the warehouse or in the factory in the sorter? The drop orientation, if it was dropped on base down, side down, top down. Deceleration levels, which is also known as G levels, and that is directly related to the fragility of the product, which is known as critical acceleration, to be discussed next webinar. and the pulse duration, just how long did it take for that pulse to happen, that shock pulse to happen. And probably the last point here is the most important point that we want to emphasize. So in webinar number 1, we talked about velocity change, and with velocity change, you could calculate something known as equivalent free fall drop height. So you want to look at pretty much how high was my package dropped and how many occurrences was it dropped at 48 inches, because that is important data that you have. So what does your ride recorder, or what does your recorder spit out? And this is a sample of a graph that I'll spit out for you. So if you look at this graph, it's telling you on Thursday, November 6, 2014, at around 1:32 p.m., this shock happened. And it was the 4th event of the recorder, which means it's the 4th drop, and it was dropped on the flat bottom orientation. And G's that it saw was around 171, and the delta V was 292. And then you do some calculations, and then you could actually get a equivalent free fall drop height with that number. And Herb is going to talk about vibration measurement right now.
Thanks, Edmund. Measuring the vibration environment obviously involves measuring vehicles. That's where it comes from. It's necessary to attach the recorder, whatever you happen to use, directly to the vehicle, directly to the source. And this goes back to what we talked about, the difference between input and response. So you've got to be able to measure exactly what that input is to the package system, and that's what the bed of the vehicle is all about. I remember seeing lots of data presented where you get these bumps and jolts and things like that, and it's obvious people were actually recording a response of a package in vibration rather than the actual input. At any rate, the recording of the vibration data inside of a package is not appropriate because it shows the response of the system to the vibratory input, not the actual input itself. And the input is what you're going to reproduce in the laboratory. So the data recorded shows, or should show, the overall vibration intensity at each frequency. And then also the overall acceleration levels, in other words, the intensity levels, and the amount of time the vehicle is actually moving. So these are the critical things that the ride recorder would measure for distribution environment quantification. And this is an example on the next slide of what that data might look like. Now, I would challenge anybody to be able to quantify that stuff from the time domain that you see on top. Looks pretty. It's actually 3 separate axes, X, Y, and Z, recorded over time. In this case, about 200 milliseconds per division or so. So it's about a second's worth of data there. But it's very difficult to put a number on it, very difficult to quantify. What you can do with that data is that you can separate it into the frequency domain, which is what the bottom plot attempts to do. And what that shows is the intensity level at each frequency. Again, it's a problem because you can't put a number on it, you can't quantify, you can't do a lot with it. So the following slide shows us what we much prefer, and that's a spectrum. Again, so that's an amplitude. In this particular case, acceleration density, PSD, power spectral density on the vertical axis versus frequency on the horizontal axis. So it tells us that each frequency, what the anticipated or the measured, in this particular case, amplitude level, G level, was at that location. The actual quantity, PSD, or power spectral density, it's kind of a squirrely one to actually define. It does make sense, and this is probably a topic for a further webinar in the future, but that's the amplitude level. It's the measure of the amplitude level that's actually used for vibration recording. So this is the overall GRMS level, which is shown at the very top, 0.39 approximately. Geez, that gives you the mean or average amplitude of that line. But that's That's also the area under that acceleration versus time pulse, or the root mean squared area. So this is the preferred format, and you can see why it's so handy, because you can actually quantify it using this particular method, whereas in the time domain you really can't. It's really almost impossible. Moving forward, if we look at the temperature and humidity data, we see kind of the anticipated results in the time domain at any rate. So we see that there are portions of that plot where the temperature is high and portions low. So this normally corresponds to the 24-hour cyclic day and night cycle. The blue line below that shows the humidity level, and we also see the same anticipated results there, namely when the temperature goes up, humidity level goes down because the air has a higher degree of ability to hold moisture at higher temperatures. So as it gets warmer, the relative humidity, in other words, relative to the saturation point, goes down, and when the temperature gets colder, the humidity goes up. So this would be a good sanity check that the data, in fact, was at least seemingly accurate, didn't have any gross errors in it. But that's a method of reading the data. It's actually done in a number of different studies, so I would not encourage someone to go out and measure the temperature environment. It's been done many, many times, and just do a good literature search and you'll find out exactly what that is. Edmund, can you tell us about these standards versus the studies?
Definitely, Herb. So if you think about, what we talked about maybe 30 minutes ago, FPL22 and the Maid Study, we have, some good data here. And what FPL22 says that for each trip, it was around 18% of the drops were over 14 inches. And then around 6% of the drops were over 36 inches. The Maid Study, which is, much more up to date, you could say, just because it happened 40 to 50 years later, and the 14-inch drop actually dropped from 18% to 5%, and the 36-inch drops happened, or it dropped from 6% to 2%. Now, when you're designing a package or when you're testing to a standard, let's see how these numbers compare. So in the red table, we have 4 very prominent standards that are pretty much people run here. ASTM D4169 AO1, ASTM D4169 7386 AO1, ISTA 2A, ISTA 3A. So if you look at the number of free fall drops required, okay, they're comparable to what the study showed. But like what Herb said, it also is dependent on what G level the study was set at. For instance, only record G levels over 5 Gs. And if that's the case, you would have a ton of drops, as opposed to record G levels over 10 Gs or 15 Gs, then you would have a lot less. But more importantly, let's look at the percentage of drops that are over 14 inches and over 36 inches. So if you look on the 14-inch column, every single standard has 100% drops over 14 inches. And then if you look at the percentage drops over 36 inches, 4169 has 8.33%, 7386 has 5.5%, and then ISTA 3A has 5.8%. ISTA 2A actually has 0% because all the drops are from 32 inches. And then so at this point, you might ask yourself, okay, so why are we beating up our packages so much? And the reason for that is because when you're testing a package, you definitely want to always test for the worst case. You don't want to have damage on that, 1% or that 5% of shipments, because, damage, you could say, is not good. And we definitely want to cover all our bases, to say the least. So that's for drop testing. And kind of sort of similar to vibration testing, you ask yourself, this is the same plot that Herb showed, but on this plot, it was a 0.392 GRMS overall envelope. And if you look at the 4 standards that I just talked about, every single profile is, significantly above that and more intense than that. And kind of sort of the same reason is because when you're shipping something with a vehicle, you never know which path you're going to take, which route you're going to take. So they pretty much have to envelope every single possible outcome, just because you don't know how and where you're going to ship. And that's why these intensities are quite quite more significant than what is recorded. And another reason why is because when you're testing in the lab for vibration, you're definitely trying to accelerate your distribution environments. So typically when you ship something, it's going to take more than, 5-10 hours. But then anytime you're testing in the lab, typical tests are around 2 and 3 hours. So you're definitely trying to either shorten your time by a significant amount. And this brings us to our last slide and our conclusions. And if there's anything that you should take after today's webinar, you should definitely define your distribution environment to properly package your product. Without defining your distribution environment, you're kind of shooting in the dark here. You might be underpackaged, you might be overpackaged, but you don't know because you don't know what your package sees when it gets shipped out. And hopefully today's webinar was very informative. And at this point, we have questions from the audience. Greg?
Thanks, Greg. I do want to make sure that all of our attendees are aware that our next series on number 3 of 5 in this particular sequence of protective package design and testing will occur in May, and it will cover the topic number 3 shown there, determining the vibration and shock sensitivity of products. We hope that this presentation has been helpful and that you're able to use this information to refresh your memory when the situation demands it. We will also continue to answer questions as they might occur, and also that the webinar in May will focus on determining vibration shock sensitivity test methods and the results and the information obtained from the process. Finally, I do want to emphasize that while we, in today's webinar, while we did focus on impacts and vibration and the measurement of those, we did not significantly touch on the measurement of temperature and humidity extremes or altitude levels or compression levels. But this information is readily available, and if any of our audience or customers need information on helping to define exactly what those levels are, we would certainly be happy to do that. It's relatively straightforward, readily available information. We do not suggest you go out and measure any of these things, but it's already been done for you. So thank you very much. Appreciate your attendance, and Greg, back to you.